Alrighty, in this video we are looking at inverse relations and functions. So let's begin. Our objectives are to find the inverse of a relation, determine its domain and range, and state whether it is a function. We also want to determine whether a function is one-to-one, and to use function composition to determine whether two functions are inverse functions. Let me start by describing what an inverse relation is. If a relation, and it could be called R, contains the ordered pair AB, then its inverse relation, which you would denote R to the -1 power, that is the symbol for inverse, it will contain the ordered pair BA. So what happens with an inverse is the values of the domain become the range, and the values of the range become the domain. Essentially, your x and y values get flipped. Let me show you what this looks like graphically. Here we have a relation R. And in our relation R, you have the ordered pairs 3, 1, 8, 2, 8, 4, and A, B. This is our relation. You'll see that the green circle are the x values, our domain values, and they are being mapped to their corresponding range values. If we were to look at the inverse of R, what happens is those ordered pairs, every one of them gets flipped. And you'll see in those circles, the mapping, the range becomes the domain. That kind of orange circle is now the domain, and the green circle is now the range. And your points are now 1 going to 3, 2 going to 8, 4 going to 8, and B going to A. So the domain and range, they're switched, and that is what will give you the inverses, domain and range. Let's say that we have a relation Q with those ordered pairs, and then it describes the vertices of a quadrilateral. What we're going to do is find the inverse of Q, and then graph both Q and its inverse in a coordinate plane. Well, to find the inverse of Q, all we have to do are switch the x and y values. So the first point is now 1, 2. The second is 4, 1, then 2, 6, and 4, 5. All we've done is flip the x and y values. Let's look at this graphically. When you do that, when you take and flip the x and y values, the blue is what we started with. And after flipping, you have that red object. If you could imagine folding that graph along that dotted line, you would see that we have a perfect reflection on either side of that dotted line. The graph of that inverse, the red one, is a reflection of the original relation, the blue one, across that line, and that line is y equals x. This is true of all inverses when graphed. They will always be a reflection of their corresponding relation. So it's kind of a cool property there, and one that we need to be able to recognize. Now, we've looked at just a relation where you have ordered pairs and finding the inverse, but what if you have a function and you want to find the inverse of a function? To do that, you would first want to express the function in terms of x and y. So instead of using function notation, use the y. So f of x is really y equals 2x plus 4. Then what we have to do is in that function, go ahead and flip x and y. So now it is x equals 2y plus 4. But that's not how we write an equation. We always have it in terms of y equals and then the rest of the rule. So we need to solve for y. You would first subtract 4 from each side and then divide by 2. If we simplify that, we'll have y equals 1/2 x minus 2. That is the inverse of our function f. Let's do another together. We're going to find the rule describing the inverse of this function g. So again, we want to express our function as an equation with y and x. So g of x, that function is really the equation y equals x squared minus 2. Then comes the flipping, the switching of the variables. The inverse of the function g would be x equals y squared minus 2. This is now the point where we need to solve for y. And to do that, you would add 2 to each side. And then you would be taking the square root on each side as well. And when working with square roots, you are not certain if what you're working with is going to be a positive or negative. You don't know if y was a negative value squared or a positive value squared. You would get the same result. So you have to make sure and put out there next to the square root symbol that it could be a positive or negative root. And there you have it. That is the inverse of our function g. I have a definition here for you that will help us determining one-to-one functions, which I'll define in just a moment. If you take a horizontal line and it can be drawn through a function f and only touch one point on that graph at a time, then the inverse, which would be f to the negative 1, will be a function. This is kind of similar to your vertical line trick. It's just a little test we use to help us. Let me show you this. Here are the function f from our previous example and its inverse. You can see that the inverse, that red graph, is a function. You could very easily run that vertical line test across and know that it is a function. But what if you didn't have that red graph there yet? What if all you had was the original function? Well, you could determine it just by looking at the original. If I run this horizontal line across that blue graph, it was only touching one point on that blue graph at a time. Because of that, we know that the inverse is a function. You wouldn't even have to graph the inverse if you knew the graph of the original. Let me contrast that with the g function from our previous example. If you take a look at your g function, it is a parabola. And parabolas are functions. But look at that inverse. It is not a function. And you would know that just by running this horizontal line across that blue graph. Do you see how it's touching two places right now? Because that horizontal line touched two places on your blue graph, you know that that inverse is not going to be a function. And when you have a function whose inverse is also a function, it is said to be a one-to-one function. So that f function from before is one-to-one. Now I have another term for you. Definition, I should say. If a relation and its inverse are functions, then when you compose the f function with the inverse of x, it will give you x. And similarly, if you compose the inverse function with the original function, it will give you x. They essentially undo each other. Let me explain this using an illustration. Let's say that we have the inverse function composed with the function f at 10. You could rewrite that using the definition of composition as the inverse of f, and then inside of that, the inverse, f inverse of f at 10. Sorry, that's kind of a tongue twister. F inverse of f at 10. In this little graphic you can see, that means take 10 and plug it into the f function. That would be 2 times 10, which is 20, plus 4, which gives you 24. That is the output there. Now that is what gets plugged into the inverse of f. Plugging in 24, half of 24 is 12, minus 2 gives you 10. That was our x value that we were evaluating for, and that is what the final result was after the composition. So these functions, when you compose the inverse and the function, it undoes all of the work and gives you back what you started with. They have undone each other and generated what you started with. It works the same if you take the function f and compose it with the inverse of function f. That would be the function f of the function f inverse at 10. Graphically, that looks like take 10 and plug it into the inverse of f. So half of 10 is 5, minus 2 gives you 3, and that's the output there. Now 3 is what gets plugged into your f function. So that would be 2 times 3, that's 6, plus 4 gives you 10. And again, all the work that was done is essentially undone, and the output is exactly what you put in. These inverses, when composed, undo each other. So composing a function with its inverse will give you the original input as the final output. And that is all.